are between 1/2 inch to 3/4 of an inch tall, or 5 to 7.5 feet to scale. We captured video from mornings like this one, where the air and surface temperature are only a few degrees apart, with this morning's air temperature at 15 degrees Fahrenheit and the surface temperature at 18 degrees, and the light from the distant objects, on both the large and small scale, is able to arrive to the viewer in full. And this evening, with 50-degree air and 52 degrees surface temperature, which again allows the light from the distant objects to arrive to the viewer in full. We'll also show you clips from various days when the light from the distant objects does not arrive to the viewer in full and the objects appear to sink. During the day, the surface will typically be warmer than the air above it, so we consistently witness this sinking effect throughout the day, day after day. Here's an example of the red Hot Wheels car one evening when the light from the car arrives to the viewer in full. During the day, however, the car appears to sink. We have to raise the viewer height in order to intercept the light from the car as it refracts upward. And as we lower the camera, the car disappears again. We'll take a look at clips from both scales during the morning, evening, and day and observe the similarities. Here is an evening looking at the highway when we can see this car drive by the house and camper. During the day, however, we're only able to see the top of cars as they pass by the same point. Here is our small-scale recreation in the evening when we can see the car in full, but during the day we can only see the top of the car. Here are some other cars passing by on the highway one evening. And this is a car passing by the same point during the day. Here is the morning with the blue Hot Wheels car sitting by the small house, and it can be seen in full. And here is the day that we have to lift the car up in order for it to be fully visible to the viewer. So again, as we've demonstrated on this channel many times before, sinking occurs often, day after day, even with just the slightest difference of temperature between the surface and the air. Since only a small difference between the air and surface temperatures is needed for sinking to occur, and because it happens so consistently over both land and water, this atmospheric phenomena can trick a person into thinking that they've witnessed physical curvature of the Earth's surface. What they may be witnessing, however, is the curvature of light as it travels through the air of a horizontal surface, such as Earth's plains and bodies of water.
one that's pretty obvious. The light refraction has a significant pressure change. Plus, I brought up.
I can't escape the pain, I can't control the rage. Sometimes I think that I'm going insane. I'm not against what's right, I'm not for what's wrong. I'm just making my way and I'm gone. Is the weight of the world on my shoulders? 'Cause I found a way to steal the sun from the sky. Long live that day that I decided to fly from the inside. That I decided to fly from the inside. That I decided to fly from the inside.
Ladies and gentlemen, introducing, to my knowledge, the first fully functional celestial refraction model for the flat Earth. The equation is A over 90D times point A. Okay, I'm going to explain that. So A is the measured angle you start with, and D is the baseline distance to the star's substellar point. Okay, you probably already have questions, so let's go over it. The first step for calculations is based on empirical evidence that I don't think anybody would argue, and that is 1 degree away from a star directly overhead is about 69.1 miles. That's on either model. So the question is what's changing the angle? So as of right now, it's not model dependent. So follow me and don't hate me yet. You go to the right triangle calculator, for simplicity's sake, and put in 89 degrees for your viewer angle, and you put in 69.1 miles for your baseline angle, and you will get a calculation of 3958.7 in either model. Okay. I had a comment from a guy who's saying that I just basically stole the Earth's radius, and I thought that was funny as shit, because it's this calculation or triangulation that the globe Earth stole to give them a radius. So he was exactly wrong, because he didn't understand. I don't think he did anyway. But he's thinking I stole the radius of the Earth for my model. But I repeat, it's the globe model that, because it doesn't matter whether you're on a globe or a flat plane. It's what you get if you triangulate 1 degree at 69.1 miles, which is empirical for everybody. Note, from this point forward, I'm going to use Polaris as my star for simplicity's sake. Okay, so what we have now is we have a height to Polaris and a formula. So we're going to put ourselves out on the water, and the first thing we're going to do is measure our angle to Polaris. We measure 30 degrees, exactly 30 degrees. We're going to go to the triangle calculator, and we're going to put in for our viewer angle A, 30 degrees, and for our height to Polaris, we're going to put in 3958. And we get 2,285 miles for our baseline. This is where we're going to apply our model. So go up to the model, and A was 30 degrees, so we're going to say 30 divided by 90 times our distance, 2285, times 0.30. The A is 1% of the angle. So once again, it's 30 divided by 90 times 2285 times 0.30. That comes out to 228. That's our refracted value. So we're going to subtract 228. So if you're trying to follow me, go down to the bottom right. For 30 degrees, we're going to subtract 228 from 2285, and we get 2,057 miles. Now that is our exact position on Earth. If you want to cross-reference this, I put a few of them down in the bottom left, and that's distances based on 6,170 miles. So I give a few examples I'm going to give, and you see here 30 degrees is it cross-references out to the exact same 2,057 miles. So we're going to go to 40 degrees. Well, we're going to put ourselves out somewhere else in the ocean, and we measure an angle to Polaris of 40 degrees. Okay, so we're going to go back to the right triangle calculator, and for our angle, we're going to put in 40 for angle A, and once again for height to Polaris, which is side A, we're going to put in 3958, same thing, and then we calculate. We get 3,321 miles. Okay, that is our refracted distance. That's our refracted amount. Okay, so we're going to plug that into our formula. So A over 90, A is, the angle is 40. So 40 divided by 90 times 3321 times 0.40. Okay, that's, you get 590. So you subtract that from 3,021 and you get 2731. Once again, you divide the angle by 90. So in this instance, it's 40 degrees divided by 90 times that distance that we calculated, which is 3321, times 0.40. Whatever the angle is, that's what you multiply it in the end by 1% of that. So 0.40. If it's 30 degrees, 0.30. If it's 60 degrees, 0.60. Whatever angle you measure, that's what you divide by 90, multiply it times the distance, and then multiply it times 1% of that angle. So 0.60 with a 60-degree angle. I think you get it. So all of the numbers ain't right on the dot, but all of the angles are correct. So some of them are exact, some of the miles are off a little bit, but all the angles are correct. So this is functional, and you could use it as a model out on the sea. And you could put your life in the hands of my math, and you would live. I'm just kidding, but I'm pretty confident in this model. I've got some hate already from some of the Globers, or the anti-flat earthers, so that tells me I'm pretty close over the target. But I had a couple key points I wanted to throw in, so hold off on your comments until you've heard everything. But I wanted to do 60 degrees. So we're out on the ocean. We measure our angle to Polaris, and we get 60 degrees. So we take that to the right triangle calculator, and for our viewer angle, we put in 60 degrees. And for our side A, our height to Polaris, we put in 3958, same thing. Okay, we get 6855. So we take that information to our formula, and we do 60 divided by 90 times 6855 times 0.60. We get 2792. We subtract that from our 6855. We get 4113. And we cross-reference that, and that too is exact, the exact number. So no point in checking the angle if the miles are exact. I wanted to point out what I am basing everything on. I'm basing this model on upward light refraction, and I have plenty of visual demonstrations, so I have plenty of evidence to support what happens to light over long distances. I do acknowledge it would have to be a fairly consistent gradient, but over distances that great, I don't see that as a problem when you're talking thousands of miles or even hundreds of miles of getting a consistent gradient. And I base that on the humidity gradient. The moisture down at ground level is at its thickest, and if you look into refraction, everybody who has knows that water vapor is far less dense than air. So not only does the air get colder, which some people, including Dr. John D., who got a PhD in optics, who's went out and experimented, says that the temperature alone is enough, and I tend to agree. But to me, there's no getting around the fact that the humidity would play a key role or some kind of role. That's my opinion on that. But so there is some basis in science. This is kind of a new frontier, but you can get a quote from one of the big dogs in the globe model, the king of refraction, Andrew Thomas Young, who says that the long distance refraction basically is not settled science. I'm not sure that was his exact quote, but he made it clear as day that there needs to be some work done. And I want to do a thought experiment, and it's kind of funny at the same time. So hear me out. Thought experiment. So I get every flat earther to go out to sea, and they're all in a few boats in different places, and we all use whatever device to get accurate angles and this formula, okay, to get back to where we're going, okay, without the almanac. Within reason, we're off the coast a good ways. Every flat earther on Earth is out there in the Atlantic, depending on this formula, to save their lives. So one of two things has to happen in my mind, or I demand one of two things. Okay, either we're all gone because my shit didn't work, or it did work, and anti-flat earthers have to now acknowledge, or at least drop the argument of Eratosthenes proving a freaking globe, okay, or the fact we can't get uniform distances to stars or to Polaris, and that's basically why I did this. But and all bullshit aside, I did this for because to me that was a problem, and I knew there was a solution, and nobody had did it yet. But to me, yeah, we should be able to triangulate if we can go out to sea and use these numbers. Then we should have the math. If we're gonna debate a flat Earth, we should have the math to get us to fucking shore, and we now do, and to explain the distances. But when it comes to the sextant, the height above the substellar point is not a factor in either model. So I'm not trying to give bad information, but and one other point about the sextant is you could use these consistent distances between degrees, but that is pretty much useless when it comes to longitude. And in my opinion, there's a lot of problems with longitude and the deception. To me, it wouldn't even have to be deception. It could just simply be they did the best they could with mapping the Earth. Okay, and obviously, if the Earth is a plane, then the deviations are going to be in the vast oceans. And so to me, it wouldn't even have to be deception. It could be them just doing the best they can. They're basing their distances, like, for example, the flight from South America to Australia. They're basing their speed on the globe distances. So you can't use that as proof. Okay? They are calculating their speed by what is what is speed? It's rate over time, distance over time. So if you calculating yourself, you can't calculate it without distance. So if you're calculating yourself going a certain distance, whatever time it took you, that's going to dictate your speed. So on a flat Earth, you just would have went faster. Okay, it's not that far out of reach. It's not, and it's easily a possibility that the planes are going faster. Look at the Vandy Globe race. They take 80 days to complete that race, and they have these yachts that average almost 40 miles per hour. And they're taking 80 days to go, and they only dip down below the 60th south parallel in one spot. So you're talking about 18,000 miles on a globe. What the hell does it take them 80 days? That's like averaging 8 or 10 miles per hour with yachts that are racing that average 4 times that amount. So just being conservative and calculating like 30 miles per hour, you're going to get close, 60, 70,000 miles. So if you want to go down even further, it's looking like it's matching a way bigger territory down there. And, also, there's clues in them saying the Earth is shaped like a potato. Some of that horse shit. Even the old military satellite films were saying, there's a lot of, you could check out some of my previous videos where they said that the southern hemisphere is bigger. And they had to make exceptions in their software or whatever for that reason. And that to me is just more clues, more possibilities. So I'm going to give some demonstrations of how this light, maybe not how, but I'm going to give demonstrations of it bending up, and plenty of them. And when it comes to the globe, we don't get demonstrations. We try and get demonstrations. You're going to show us liquid butane. That's the only way y'all could get light to bend. We show just opening a garage door. We'll show upward light refraction just over 800 feet. Anyway, let the examples speak for themselves. But I think you're going to really enjoy this. So let's see.